Hello everyone. So this video we start a new topics on the special theory of the relativities. Okay, in this chapter, in this topic, I think it's quite new for several people. So we start with the basic of the principle of the Galilean relativities. So you will learn that the relativity it's not the new thing. I mean, it's come since Galileo times. Then we are talking about the Macpherson-Morley experiments. So we are starting to the new era after Maxwell Equations. So there's experiments and try to prove for the medium that light is traveling. Okay, and then this thing bring to the Einstein postulate, Einstein principle of the relativities, and then we start on the consequence of the special theory of the relativities. So this including the velocity transformations, time dilations, length contractions. But in the lecture, we will start from the principal thing that come before the Einstein postulate, which is the what we call the Rollins Transformations. Okay, and we use the Rollins Transformations in after that to explain all of the consequences of this special theory of the relativities. And at the end, we will discuss about the kinematic thing, so related to the relativistic linear momentums, relativistic energies, and maybe a short introduction to the general theory of the relativity. But it's going to be very short. We will not focus in this class. Okay, and the class is focused on the special theory of the relativities. Okay, so let's start. The principle of the Galilean relativities. So let's imagine we are discussing about the situation that you have observer into reference frames, and one of that it's or both is have the relative velocity as a constant. Okay, so we are talking about the two frames, and that's what we call the frame S and the frame S prime. Okay, and one of that is traveling with the constant velocity v with respect to another frames. Okay, so in these examples, there's a person sitting on a train, and the train is traveling with the constant velocity. This is just the ideal situations. And another one sits outside. Okay, so the question is that, can you say that you are moving or not? Okay, if it's really moving with the constant velocities and you close your eye, you will not feel anything. You don't really know what's going to happen. You don't know that you are moving or someone outside you is moving. Okay, you will know when you will know that you are moving because of the train deaccelerate or accelerates, and then your body still keep your previous velocities, and then when it change, you see, I mean, the effect of that. But if you are sitting, close your eye on the train that traveling with the constant velocities, you cannot really say that you are moving or outside. Even you open your eye and looking around, and I mean, without any social logical reasons, you will not know that, okay, you're moving, or the tree, the mountain, the river outside is moving. Okay, so it's not possible to say that which one is moving if both frames have the constant velocity relative to each other's. Okay, and then when we say that I don't really know that I'm moving or another one is moving, in physics way it means that you cannot really say that which one that is moving, which one is have different law of physics, because both frames will have the same law of physics. They are no different at all. Okay, so the Newtonians mechanic that used inside the train. It's still the same Newtonian mechanics that used outside. Okay, so that is the principle of the Galilean transformations. And you have two reference frames that we call the inertial frames. So one is traveling with a constant speed v with respect to another. Okay. So this is the situations. Okay, example of the situations. So you have the van, and you have the people outside the van that throwing the balls. Okay. So people on the van will feel that the ball is falling outward and then it's fall down. Okay, so nothing changed. I mean, the changing in the position in the y directions only. So there are no changing position in the x directions. Okay, so I assume this is x and this is y. So these persons, you see that the ball go up and then it's fall down. Okay, it's the straight motions under the gravity, so it's go up at the highest point and then it's start to fall down because of the gravities. But for people who's sitting outside, he will see that the ball have the component in x. So it's he will see that the ball is it's going with the parabola trajectories. Okay, so it's go up as a parabola, and then when it's fall down to the hands of the people on the truck, on the van, but it's using the parabola to describe the motion of the balls. Okay, so the question is that which person know wrong physics, understand wrong in physics? The answer is that no, both people here and here understand the same law of physics. It need to, both of them need to apply the condition properly, but they still use the Newtonian mechanics. Okay, so that is the principle of that. So this imply to the statement that there are no mechanical experiments that can be detected that can detect any difference between the two inertial frames. Okay, if you have the two frames and one frame is moving with a constant velocity, another one is at rest with respect to another's, so you cannot make any experiment to say that which frame is moving. Okay, it's not possible because everything is exactly the same. Okay. What you can say is only that there is a relative motion of one frame with respect to the others. Okay, so this is what we call the Galilean relativities. Okay. Okay, so if this is clear, so we're talking about the event and the Galilean transformations. So what is event? Event is something that happens independent of the frame. Okay, something that happens independent of the frame. Okay, for examples, you see the fireworks. So that's events. You see the fireworks. Okay, there is a fireworks. You see it from the board. You see it on the car. You see it on the plane. You see it when you at your homes. You see it when you're walking. It's just one event, right? You can have different frames to describe it. Okay, so that is what we call the event, something that happened and it's independent of the frames. Then we have two events. The first event, we set it when two frames cross each other. Okay, you start to have the S frames, which is at rest. Let's say that in that way. The S prime frame that is moving with a constant velocity v along the x directions. Okay, you set the first event that when two frames cross. So when it cross, it means that you have the S frame here, and then you S prime frame here. Okay, S prime is moving here, but it's crossing the origin of the S prime. It's the same place at origin of S. Okay, so we set X in S frame, X equal to 0 and T equal to 0. Okay, and in S prime, we say that X prime equal to 0, T prime equal to 0. Okay. However, in classical mechanics, when we are talking about the times, okay, we have the statement that all the clock running at the same rates, regardless of their velocities. Okay, so the clock of the observer in the S frame is the same clock of the observer in the S prime frame. This is the classical mechanics. There are no difference. You use the clock there, you can use the time to describe the clock in another frame. Okay, so it's mean in this case T prime is equal to T. Okay, and then there is a second event when the firecracker happens. Okay, so looking on this chart, the fire happen is it's happened for the S frame. It's happened at X equal to X. On the S prime frames, it's happened at X equal to X prime. Okay, and the S prime frame is traveling with the time t, so it's traveling with the distance vt. So in this case, we can say that the X prime is equal to the X minus vt. Okay, and then if you're talking about the velocities, so velocity is differentiated with respect to time, right? So the velocity will be ux prime equal to the ux minus v. Okay, you differentiate by dt, and then you differentiate again. Okay, so it's become the second derivative of time. You get the accelerations in the S prime frames equal to the acceleration in the X frame. Okay, so in the Galilean transformations between two inertial frames, you see that you have A prime in the S frame equal to the X prime in the S prime frame. What does it mean? It means that you have the same force because the force is equal to the m times the accelerations, right? So it's ax prime and it's equal to the max. Okay, so, and this is what we call and this is what we said before, that we can use the same law of physics in both inertial frames. Okay, so this just take the note here that this is back to that there is no difference in physics in all inertial frames. Okay. So what does it mean? It means that if you want to describe any event, go back to this one, you want to describe this event, the ball go up and fall down, you can use this frame or you can use this frame. It's whatever you want. It's the same. Okay, so choose the frame that it's fit you all, easy to solve, then you use that frame. Okay, so this is the key point of the Galilean transformations. I haven't said about the transformation in y and the z-axis because there are no changing in y and z in this case. Okay, so you get y prime equal to y and z prime equal to z. There are no movement in y and z. So it's this y and z are transferred with the the velocities. Okay, so there are no changing, there are no transformations in these two axes. Okay, just note that this conclusion, okay, is true only when you have constant velocities. Okay, so we are talking about two frames. One of that is traveling as a constant speed compared to another's. Okay, if there is an expression of the frame, this thing cannot be used. Okay, it's different. Okay, so this physics survived for 100 years. Okay, there's nothing that it cannot be described in that period. Okay, it's Newtonian mechanics, let's say. So it's true in that time. Okay, and then when we start a new modern era, we start at the Maxwell equations. So this is Maxwell equations. I think this is what we have learned before. Okay, we are talking about the equations from Gauss, from Faraday's, and from amperes, and modifying amperes to the general forms. Okay, and everything together we call the Maxwell equations. And in these Maxwell equations, we get the electromagnetic wave, right? So finally we have the wave. It's traveling with the speed c, which is equal to the epsilon 0 mu 0. Okay, this is what we get from the Maxwell equations. Okay, and the c is the speed of light, 3 times 10 to the 8 meters per second. Okay, but if we compare it with the classical mechanics, like the speed of sound, the speed of the string wave, so that wave used the mediums, right? In that time, we know that there's a wave, there's a mediums, and the wave is traveling in a medium with the speeds. So Maxwell equations are based on that information also. It's based on that idea also. So the light needs to traveling with, let's say, in the mediums. Okay, so between the sun and earth, they should have the mediums, and maybe the medium is everywhere in the universe, so that light can travel. And what we call that medium as the ethers. Okay. And then if we remember, when we talking about the Doppler effect, there is a changing of the velocities. There's a relative velocities when the medium move. So light should be the same. Okay. So the speed of light have to be respective to the frame of reference of the ethers. Okay, when the ether move in different direction, the speed of light should change. Okay. There is few ideas related to the ethers. The idea that ether is stationary and partially dragged by the earth. So it's like you have a field of pool waters and you put the ball there, and when you drag the balls, some of the water is also be dragged together with the balls. Okay. Or another one is that the ether is completely dragged by the earth, and thus it shares the motion with the earth's surface. So you have the earth and the earth filled with the ethers. When the earth moves, the ether moves together with the earth. Okay, but that's maybe not popular idea. Okay, because we are talking about several stars, and each of that need to have the ether with them, and it's dragged together. So the idea that ether is stationary, so spread around the universe, and then when the earth moves, these things are partially dragged with the earth. So the mediums come with the earth. So it means that the light can always travels. Okay, it's like when you're talking on the earth's surface. You talk here, you walk, and you talk there, and you walk and you play somewhere else and you talk there. So you still hear the sound, and when you measure the sound, it's still the same speed because the air is everywhere around you. Okay, that is the same idea. So the ether is everywhere around us, and that's allow the light traveling. Okay. So if this is true, they need a proof. Okay, so they need to prove that the speed of light is different. But since the speed of light is very, very fast, I think we discussed about that, how Galileo is trying to prove the speed of light, and it's almost impossible. So we need to use something else to prove. Okay, and what we're going to use is what we call the interferometers. And that's what we have learned in the interference topics. Okay, so something, the light is traveling on two paths of the systems, and then it's go back, and then you see the fringe of the interference. Okay, so there is an experiment called the Michelson-Morley experiments. Okay, so the experiment, it's, I think we familiar with that. We didn't really discuss about this in detail when we talking about the interference, but we will talk here. Okay, we discuss here. So the experiment start that you have the light source. Okay, so the light source produce the light, so they are in phase, right? And then it's incidence of to the first mirrors, and it's split. Okay, so it's the first one go to the in the arm one directions, see the mirror, reflected, come back, refract, and then go to the telescopes. Okay, the second one, the first diffracted, okay, go out from the mirrors following the arm to distance path, go back, reflect to the telescope. So now two lights coming from the arm 1 and light from the arm 2, they sum up to each other, so they make the interference patterns at these telescopes. Okay, so when you are looking in this table, this is a Michelson-Morley interferometric setup. Okay, so you have something like light source, and then the telescope and the mirrors. Okay, I don't know which one it is. And then there's mirrors somewhere in the middles. Okay, but there's another one here that it's not present here. Okay, this is what we call the light compensations. Okay, what is the light compensations? If you looking on the light, the part, I call this is the part 1, this is part 2. Okay, so for the part 1, how many times that it pass the mirrors? So the part 1, it's go in this way, reflect, go up, reflects, right, refracts, and go to the telescope. So it pass the mirrors 1 time. Okay, but for the part 2, okay, there is a light, so it's refracted first. Okay, refracted first, so go following the part 2, go back. Okay, refracted, go back to this point, reflected, and then go to the telescope. Okay, so the part 2, it's past the mirrors 3 times. Okay, so the light compensation, to compensate the missing of the missing mirror, so it try to add 2 times that the light need to pass. Okay, so it's adding the mirror here. Okay, so this is the compensation mirrors. Okay, and then when 2 lights meet here, so they make the interference patterns. Okay, so this is the principle of the Michelson-Morley experiments. And if you see on this figure, so it's putting on one of the plate that this thing can rotate. Okay, so we discussed that why it need to be rotated later. But this is how the experiment is set up. Okay. Again, that this experiment is set to detect the motion of the Earth relative to the ethers. Okay, let's take the note that the Michelson-Morley experiments. This is to study the motions of the Earth relative to the ethers. Okay. Okay, so we start to do the short calculations. Okay. Let's say let's look on these figures. So there is sorry, I think I forget one thing to mention. So when we set up the experiments, we don't really know where the ether direction is. So there are no idea about the ether winds at all. Okay, Michelson and Morley don't really know about the direction of the ether winds. So it can be in this way, it can be this way, whatever. Okay, and that's why the experiment needs to be set that it can rotate. Okay, so they need to set how to say they need to set they need to do experiment in set. Okay, so they need to do different set depend on the orientation of the tables. Okay, so the first time this is for example maybe the table is in this direction. This is the top view, look up. Okay, and then they need to start to rotate because they don't know that which way that the ethers will come. Okay, and then they do the experiments, they take a note, they take a pictures, recording on the film, whatever they're doing for the fringe of the interference fringe that they see on the telescopes. Okay. Okay, so let's do calculations. I start with the arm tools, the part tools. Okay. For the arm tool. Okay. The light is traveling with the speed v, with the speed c. Okay, and the ether wind is speed v. So for the first trip, it's go opposite way with the wind. Okay, so this is the light with the speed c, and this is just the ether wind speed v. Okay, and when it's go back, so this is the speed v is the same, and this is the speed c. Okay, so the time that it's traveling on arm 2, okay, it's gonna be the distance. Let's set this one as the L. Okay, so it's L divided by the relative speed, so c minus v, and plus with the L divided the speed c plus v. Okay, c minus v is the first trip, and then it's go to the millers, and then c plus v, it's go back from the millers. Okay. Again, since we don't know, so what we are trying to measure, it's not just one setting, so they need to rotate and do the experiments in all directions. Okay. So we make a common denominators. So c plus and c minus, so it's finally you get c square minus v square, right? On the top you're gonna get, let's do it on the overhead, so it's lc plus v, and this is lc minus lv. So it's we get 2LC. Okay. And then we make arrange the term a bit. This is just to make it easy for the later calculation. So don't worry if you don't think about that. I mean, it's just arranging the term. So it's get 1 minus v square over c square to the power of the minus 1. Okay, so this is on arm 2. Okay, now we talk about the arm 1. Okay, so for the arm 1, you have the ether wind with the speed v. Okay, you have the light with traveling with the c. So this is the relative velocities. Okay, since we know that the light is traveling straight, so it's mean that if you have the ether wind, so the light should be going in these directions, and then it make the relative in straight in the forward or straight directions. Okay, so the size is become c square minus v square, and then you take the square roots. Okay, and since this is all the same thing between go and go back. Okay, so the delta t of arm 1, it's gonna equal to L divided by the square root of the c square minus v square. Okay, and we do the same thing, so we do 2L over c. So we're gonna get 1 minus v square over c square to the power of half. Okay, so we can find the difference. Okay, so the delta t gonna become the delta t in arm 2 minus the delta t in arm 1. Okay, so you this is equation 2, and this is become equation 1. Okay, let's set it in this way so it's easy. So you get 2L over c. Okay, and you get 1 minus v square over c square to the power of minus 1 minus 1 minus v square over c square to the power of half. Okay. Then if we consider that v over c is much smaller than 1, okay, so we can use the binomial expansions. Okay, 1 plus x over n, it's become 1 plus nx and blah blah blah. So we keep only the first the second orders nx. Okay, and maybe we call it the first order with the x to the power of 1. So the delta t's become 2L over c. Okay, so the first one is 1 plus v square over c square, right? We use the binomial expansion because we assume that v over c is less than 1. Okay, so we can expand it. And the second terms become minus. So it's 1, and then this is plus, and we miss it minus half of the v square over c square. Okay, so this plus and minus 1 cancel. So finally, you're gonna get L v square divided by c to the third. Yeah, approximate because we do the binomial expansions. Okay. So this is a time difference. Okay. If we would like to convert this to the distance, the difference of the path difference. Okay. If you're talking about the path difference. So this is time, right? So to make the path, you need to multiply by c. Okay. So finally, you will get the path difference is L v square over c square. Okay. So from this formula, you will see that it's depend on the ether wind, right? The ether wind manifests as a path difference. Okay. Great. So this is done. No, we don't really compare anything yet. Okay. So we need to do experiment, another setup. So the question is that how can we set another things? So let's see in these situations, right? Sorry. Okay. What are you stopping? Okay. So so this we see only one setup, right? And then if we make another setup, which one that it can make the almost the same thing, almost the same setup, something that can be replaced with each other. Okay. So if let's go back to this setup. The ether wind here, you see that it need to traveling. So one is parallel to one path, right? And another one is perpendicular to another path. So this is a key point of two arms. This is the key point that we make the calculation here. Okay. So another setup is try to turn it 90 degrees. Okay. So if you turn it 90 degrees, turn 90 degrees, okay. Arm 2 gonna be arm 1, and the arm 1 gonna be arm 2, right? Okay, so if you turn it 90 degrees, okay, so the arm 1 gonna be on the way of the ether winds. Why arm 2? It's gonna perpendicular to the ether winds when the light is moving. Okay. So if we do in this way, we're gonna have almost the same, right? Except that when you try to subtract it, okay, it's just moving the term. So you can calculate the shift, okay, between the first setup, I call it delta lambda, and another setup, the delta lambda prime. Okay, so the delta lambda, this is the the path difference. Okay, and the delta lambda primes coming from the turning of the 90 degrees. Okay, so this gonna equal to the 2LV square over C squares. Okay, so this is the total shift, the path difference that you're gonna see from two setup. Okay, then if you would like to see the shift, you can just use the divided by the lambda. So you use the path difference, d psi theta equal to the n lambda, right? So you would like to find the n, you would like to see the shift, you divide this path difference by lambda. Okay, so this is what you're gonna get. Okay, so this is from the first setup. Okay, and then you turn 90 degrees. You see the shift. Okay, it's small, but you can use the number to calculate. Okay, okay, I go back, putting the shift, the numbers here. So you see the shift in lambda, in delta lambda minus delta lambda prime equal to the 2LV square divided by C square. And then you should see the shift in N to the 2LV square C square over lambda. Okay. In the Michelson-Morley setup, they use L equal to the 11 meters. V, which is basically the speed of Earth around the sun, equal to the 3 times 10 to the 4 meter per sec. Okay, so V, this is the speed of Earth around the sun. Okay, lambda is 500 nanometers. Okay, so if you use this number, see, you know that you get the delta n equal to the 0.44. Okay, so this is what they expect to see the shift. Okay. I don't know that the resolution of that experiment. So this is from the book. They say that this experiment can be able to detect the fringe shift down to the 0.01. So clearly, if you use this setup with the shift of 0.44, you should see that. Okay. However, they detect no shift in the fringe pattern at all. Okay, so this is a very key point, that they cannot really detect the shift in the fringe patterns, even they turn and whatever. I mean, all the setup they are doing. So what does it mean? This is something, it's the basic, that you make the assumptions and then you don't see it. Okay, so what you can do, you say the assumption is wrong, or the assumption is not wrong, but you need to do what we call the ad hoc assumption to that. Okay, you need to modify something in your assumption, and that can explain your now result of the experiments. Okay, so in this case, they expect to see the shift. They don't see the shift. They can say that something is wrong, or something is missing on the assumptions. Okay. So in 1890s, Fitzgerald and Rollins tried to explain this now result by making the ad hoc assumptions. So what they say is that the length of an object moving at the speed v would contract along the direction of the travel by these factors. Okay, so the length of the object moving at the speed v would contract along directions of travel by these factors. Okay, so this result of the contraction change the length in one arm, so to make that there are no path difference at all happens. Okay, so when the experiment is rotating, there are no path difference, so they cannot really see the shift of the fringe. Okay, so this is the very ad hoc assumptions. Very smart thing, they say, okay, when the object is moving with the speeds, so the length should be contract by these factors. Okay, so so in this case, it will contract this term, okay, by that factors. And then when this term is contract by 1 minus v square over c square and the square root of that term, they will not make any part difference between this and this, okay? Then they cannot see the friendship, okay? Fitzgerald and Rollins never say that either is wrong. They just say, yeah, if you have this curve, they're traveling at the speed v, the length is contract, and that's what they expect, okay? So with that ad hoc assumptions, Maxwell equation can be described, can be used to describe the experiments. So there's, that's we discussed, mentioned about these Rollins and Fitzgerald, and also the Joseph Lamont that developed this theoretical approach of that. Okay. And then Lamont and after that Rollins derive what we call the Rollins Transformations. Okay, this name is not named by Rollins or Lamont, so it's named by one of the physicists, Henry Postulate. Okay, so he tried to describe the electromagnetic theories with presence of these transformations, and he called this transformation as Rollins Transformations. Okay, so this is very beginning of the special theory of relativity. So it's not pop up from the space from the brain of Einstein. No, it's not. It's coming from the long developments. Okay, starting from the Maxwell, doing experiment by Michelson and Murray, try to make the null hypothesis from try to make an ad hoc assumption on the null hypothesis from the experiments, and you get the Rollins transformations. Okay. So this is a big revolutions of the theory of the electromagnetics. Okay, but this still in the scope of the electromagnetics. Okay, if you're looking on the Postulate paper, so he didn't talk about something else, but he just said that this is in French. So he talking about the electromagnetic, which will not change, okay, with the transformation, and this is what he called Rollins transformations. Okay. So let's go next. So the postulate in the special theory of the relativity. So when Einstein come, he said, yeah, but at the end, ether is not necessary things. Okay. So he said that the ether are unnecessaries. Okay. And then the conclusion from the Maxwell is predict what you get from the Maxwell equations is that the light should have the fixed speed of okay, just one value, independent of the velocity of the observer. Okay. So this is a starting point of the special theory of the relativities. So he write two postulates. Okay, the postulate is something that you cannot, you don't need to prove. It's something that you believe that it is. Okay, so these two postulates. The first one is basically the basic of the relativities since Galilean. So the law of the physics must be the same in all inertial reference frame. So it's nothing changed. We write it from the Galilean transformation. The second one, the constancy of the speed of light. So the light have the constant speed, 3 times 10 to the 8 meter per second in all the inertial frame, regardless of the velocity of the observer. Okay, so observer in all the frames can measure the speed of light and they will get exactly the same value. Okay, so this is from the Albert Einstein. But after he published this, I think in a few years later, he accepted that this also the result from the Rollins transformations. Okay. What time is it now? It's 50. Yeah. So let's finish the Rollins transformations. So The Rollins transformations. So we're talking about the same situation as the Galilean transformation. So you have two reference frames. Okay, one is moving with a constant speed with respect to another. When the two frames cross, you set up the times. Okay. So when the two frames cross, you say, yeah, x equal to 0 and t equal to 0. Okay. Another one, x prime equal to 0 and t prime equal to 0. Okay. And then when two frames cross, you set the clock and you say the light is emitted. Okay. After the light is emitted, the light signal is detected. Okay. So you start from Galilean transformations. X prime, right, equal to the x minus vt. And then if you would like to say the x equal to the x prime plus vt. T prime. Okay. So in these transformations, the time is different. Okay, it's beyond the classical model that the time on two frames it's the same. So you keep the time is different. Okay, each observer have their own clock, and the clock it's not the same. Cannot measure, will not measure the same rate of the tick. Okay. Then what we do from this is that the observer can see also the different. Okay, so when you try to measure something, right, like you try to measure the speed of light, you try to measure the length, for example, one observer will say, no, you did wrong. Say to another observer, yeah, no, you did wrong. Your stick, your meter stick, it's wrong. It should be shorter than that. Okay, and this is the what we get from the Rollins transformations, right? So everything it's moving along, so it's shortened by the factors. Another one will say, yeah, but the people who wrong is you, not me, right? So imagine, so you have two observers, so one is moving. Let's say one is at rest, one is moving. If you're talking about the people at rest, you say, my meter is correct. The meters of the people is moving is wrong. But then if you're looking on a different point of view, you're looking on the point that another observer think that he is not moving. Another one is moving backward like this. And he say, yeah, my meter is wrong. My meter is correct. Your meter stick is wrong. Okay. And following the Galilean transformation, you cannot really say which observer is moving. It's relative, right? It's the same because their law of physics is exactly the same. Okay. So when you say that, it's mean, okay, it's wrong by some factors. Let's put the factors there. Okay. And it's a symmetric one because everyone say another person is wrong. Okay. So in this case, what I can summarize that each observer see difference length. Okay. Then you multiply it to each other. So you get x prime equal to the g square, right? x prime plus xvt prime minus x prime vt minus v square t prime. Okay. Then you divide it by x and x prime, so you get 1 equal to the g square 1 plus vt prime over x prime minus vt over x minus v square tt prime over xx prime. Okay. So go back to the figures. So we detect the light as time t prime for the observer S and the time t for the observer in the S frame, right? So it means that the light is traveling x in the distance x, okay, at time the light is traveling with the distance x in the time t prime. Okay, so for the S prime, the distance x prime equal to the v, which is c, and time t prime. For the S frame, the light is traveling at length x equal to c t. Okay, so what you get is that t over x is 1 over c. Okay, and this is the same for the S prime, t prime over x prime. It's 1 over c. Okay, so t prime over x prime, it's 1 over c, t over x is 1 over c. So the term can cancel. Okay, and this term become c squared. Okay, so finally what you get is 1 equal to the g square 1 minus v square over c square. Okay, then the g equal to the 1 minus v square over c square to the power of the minus half. Okay, and this is what we call the Roran factors. Okay, so finally for the Lorenz transformation, the x prime can equal to the Rollins factors 1 over square root of 1 minus v square over c square of x minus vt. Okay. Okay, great. So now you can transform x, right? Y and c, we don't need to talk about that because it's perpendicular to the for the moving. So y prime and c prime, it's the same. Okay. So we are now talking about t. Okay. So if we need to talking about t, let's me think about it. What should I do? Starting from the another equations, so x equal to the x prime plus vt prime multiplied by the Rollins factors. Okay, so x equal to the x prime, so x prime is gamma x minus vt, okay, plus vt prime to the gamma. Okay, so you use this one, put the x prime, okay, to this term. Okay, and then what you will get is x gamma squares, right? You multiply that, minus vt gamma square, right? Right, plus vt gamma, okay, and then we divided all the equations by v gamma, so we're gonna get x over v gamma, so divided by v gamma, so we get x gamma over v minus v gamma, so t gamma plus t prime. Okay, so now you get t prime equal to the, move everything to another side, did I do something wrong? Not really. T gamma plus x over v gamma minus x gamma over v. Okay, so if I did something wrong, plus x v gamma minus x gamma. Okay, great. Then we set t gamma, and then plus you put the gamma out, so it's become x over v gamma square divided by x over v. Okay, in this bracket you bring x over v out, it's become 1 over gamma square minus 1. Okay, so what is it? So it's x over v, right? The gamma square is what? So you get 1 minus v square over c square. You put it on back, so it's get 1 minus v square over c square and then minus 1. Okay, so finally you get cancel, v cancel, so you get minus xv over c square. Okay, so this is a term xv over c square. Then finally you get t prime equal to the gamma t minus xv over c square. Okay, so this is the Rollins transformation of the terms. Okay, if it's unclear, you can try to go back and prove later following this guideline. Okay. So this is the Rollins transformation of the positions and the Rollins transformation of the time. Okay, great. So in summaries, what you get, okay, you can type it, you can write it in the next one for the summary. So so the coordinate transformation between event found in S and S prime can be related to this following equation. So x prime equal to the gamma x minus vt, okay, y prime equal to y, c prime equal to c, and t prime equal to the gamma t minus xv over c square. Okay, and if you would like to do the inverse Roran transformations, what you should do is just switch prime and unprime and switch the sign of the v. Okay, so you're gonna get x equal to the gamma x prime plus vt. Okay, y equal to the y prime, c equal to the c prime, t equal to the gamma t prime plus xv over c square. Okay, so this is inverse Roran transformations. Okay, so this is to prove about the Roran transformations. After this, until almost the end of the topics, we're gonna starting from this one. So you need to be familiar with these equations. Okay, it's a key of the special theory of the relativities. Okay, you use it to describe several things from this one. Okay. What time is it? It's 1 hour and 10 minutes roughly. Okay, let's finish this slide so that we can clean up things. So we're starting from the new slides that continue from this one. Okay, so we have 2 slides more to go. So at this point, okay, we have a really key point of the special relativities. So we now start to talking about the consequences from that, from these transformations. So I pick up the first one, which is called the Roran Spirocity transformation. So this is not the first topic about the consequences in the book, okay? But I think this one is important that you're gonna use the result later, okay? So we're starting from this one. So now we are talking about the events for the object motions. Okay, so the object starting from x1 t1 moving to x2 t2, okay, or x1 prime to the x2 prime. Okay, so using the Lorenz transformation, so we get x1 prime equal to gamma x minus x1 minus v t1. Okay, and then you have the x2 prime equal to the gamma x2 minus vt2. Okay, and then you have t1 prime gamma t1 minus vx over c square vx1, right? And t2 prime equal to the gamma t2 minus bx2 divided by c square. Okay, so now you want to see the difference. Okay, so you get you do x2 minus x1, x2 prime minus x1 prime. Okay, x2 prime minus x1 prime, so we call it the delta x prime. Okay, what is this? What is it? It's gamma delta x minus v delta t, okay? And t2 prime minus t1 prime, it's delta t prime, it's gamma delta t minus v delta x equal divided by c squared. Sorry, not equal. It's quite late tonight that I'm making this video, I'm sorry. Okay, so you get this pair, okay? Why this thing is special? Because you see that this is basically the Rollins transformation, but the pair of the events, okay? So you can see that the pair of the events follow the Rollins transformations. Okay. It's not only the transformation from the coordinates and time, but the pair of the coordinates and time also following the Rollins transformations. Okay, and this is very important. You're gonna see in the next video that this thing is used several things. You use it is for the simultaneously the simultaneities, length contractions, time dilations, and several things, the kinetic stuff. Okay, so we now would like to describe about the velocities. Okay, again, but I said that this is very important. Okay, you need to be familiar with this one. Okay, so today when you go back after you finish this video, make sure you understand the Rollins transformations, the inverse, if you can do that, and the meaning of the pair of the events that still follow the Rollins transformations. So now we would like to talking about the velocities, right? So the ux prime basically it's the change of the positions divided by the change of the time. But be careful when we're talking about the velocities. Normally we're talking about very short period of time, right? It's derivative. So derivative, it's mean that dx by dt, it's x, right? If you remember dx by dt, it's the limit that delta t equal to 0 of f, right? X at t plus delta t minus x t divided by the delta t, right? And you approach this one to 0. But in these situations, the delta x and delta t, it doesn't need to be small. It means two events happen in a different place and time. You want to do pair of that one. You want to pair it. Okay. So it's not need to be small. Okay. But we can use this definition first and then we just take the limit later, which is this is fine. Okay. So the delta x, what does it? What is the delta x? It's gamma delta x minus v delta t divided by the gamma delta t minus v delta x over c squared. Okay. So we cancel the gamma. So what we would like to do is try to make the compact one. So you divided by 1 over t and 1 over t, 1 over dt and 1 over dt there. Okay. So the first term, the delta x over delta t is u, right? It's a velocity of x minus v and 1 minus v ux over c squared. Okay. So finally you get the velocity as seen from the observing s prime equal to the ux minus v 1 minus v ux over c squared. Okay, and if you do the inverse, if you would like to measure the velocity in S with the information from the S prime, so you get ux prime plus v 1 over 1 plus v ux prime divided by c squared. Okay. Okay. Sorry, maybe I will need to move this one. C come, okay. Fine. I will. Sorry, I just need a space, a little space here. Okay. Then now we're talking about the x. Okay. How about y and z? Okay. So you have uy prime, right? It's gonna be equal to the delta y prime divided by t, right? Sorry, delta t prime. So delta y prime, it's equal to the delta y. So it's the same, right? However, the delta t prime is these factors. Okay. Then you do the same. You divide it by the delta t in both numerator and the denominators. So you get uy divided by gamma 1 minus v ux over c squared. Okay. So this is the uy prime. And then you're gonna get the same thing for the uc prime. So this is uc divided by gamma 1 minus v ux over c squared. Okay. So this is the velocity transformations. Okay. So you would like to measure the velocity on one frame with the information from another frame. Okay. If you would like to know the velocity seen in from the S prime frame, and you know ux, and from the S frame you can calculate that. Okay, and do it in vice versa. Okay, so last one is about the examples of this transformation. So the example is to make you a very clear picture. So for example, you are observer. Okay, you observe the biker. Okay, but he bike very fast. It's 0.8 of the speed of light. Okay, and then he throw the ball. The ball is also very fast. It's 0.7, 70% of the speed of light. So the question is that this person, how he see the speed of the balls. Okay, we don't need to talk about the the biker who see the speed of the ball, because he at rest with the frame. So clearly he will see 70% of the speed of light with this one. However, this person who's standing here, so with the Galilean transformation, he will see 1.5 c, right? This is the speed of the ball. Okay, but this is not allowed, right? This is not allowed in special relativities. Okay, object cannot have the speed larger than the speed of light. The speed of light is very large, and it's the largest one that we can have. But be careful. I said the speed of light, it doesn't mean it need to be light. It can be anything that have that speed. Okay, for example, you're talking about a gravitational wave, it have that speed. Okay, so all the objects have the limit of the speed. So that speed is the speed of light. Okay, the photons, which is the light particle, it have that speed. Okay. So we need to use the velocity transformation here. So what we're going to use is the inverse one, right? Because we're talking about people in the S frame, the rest frame, and looking on the moving frame in this picture. Okay. So you get the ux equal to the ux prime plus v 1 plus ux prime v divided by c square. Okay. So on the top, you're gonna see 1.5 c, right? This is the sum, and this is the Galilean transformation. But from the denominator, you're gonna have 1 plus ux prime multiplied by v, so 0.56 c square over c square. Okay, so you get cancel. So finally you get 1.5 c divided 1.56 c. Okay, so clearly this is less than 1, right? Oh, sorry, you should not have c and on the denominators. So clearly this is less than 1. So finally you will get like 5 something, 95 or 96 c. Okay. So this is from the SR point of view. Okay. So the object cannot have the speed larger than the speed of light, and this follow the Einstein postulate. Okay. Great. So this is done for the first video. I think we're gonna have the second and the third one. The second one gonna be quite a long video. I record in Thai for another course. It's about 2 hours. I said that I think that it's gonna be roughly the same for us. But the key point, the really key point, is these Rollins transformations and the pair of the events. Okay, so I know that you're gonna have the exam on Wednesday, but I hope that you still have time to study this one. And I try to release the second video by the end of the week, and maybe the third one. Okay, so that you're gonna have chance to have a look and familiar with that before we go doing the exercise next week. And the time for the exercise next week, maybe we have to change it to Wednesday, so that you can have time to finish the video of the relativities before the exercise day. Okay, but that's we're gonna discuss in the chat on the Facebook, and I will make an announcement at the Blackboard, on the Blackboard also. Okay, so today let's go back again. Today we understand what we call the relativities. Okay, the concept. We're talking about the Galilean transformations. We are talking about the experiment to confirm about the light speed. Okay, and the most important one that we have today is first the postulate from the Einstein. The postulate that the law of physics must be the same in our initial reference frame. This is a postulate since the Galileo time. And then another postulate which is new is that the speed of light is the largest speed that the object can have. Okay, nothing can go beyond this speed. And we're talking about the Rollins transformations. Okay, and we talk about the pair of the event that also follow the Rollins transformations. Okay, I think this is all for this video. See you in the next time. Thank you. Bye-bye.